Okay, so going back to the event itself, we have with us today Patrizia Carpenteri, Anqi Chen, Eirini Kotrotsou, and Mattia Bernardi, who will talk to us about design against terrorist threats. Patrizia joined ARUP as a senior consultant at ARUP Resilience, Security and Risk Team in June 2019. She has extensive overseas experience managing projects involving structural, earthquake, and blast engineering topics. In ARUP, she specializes in the management of blast design for facades and structural elements, dynamic response of buildings, and hostile vehicle mitigation strategies. Anqi is a consultant within the same team. After gaining his PhD in blast engineering at Imperial College London, he has done research work on blast effect on structures, floor vibrations, and structural steel design. Since joining ARUP in 2020, he has worked on a variety of projects related to the protective design of buildings in the public and infrastructure sectors. Eirini is a senior consultant within the same team as Patrizia and Anqi. Her academic background is in structural engineering with a focus on earthquake engineering and the dynamic response of structures. Her work in ARUP focuses on developing strategies and designs that enhance the resilience of buildings, sites, and communities against terrorist threats, with a focus on facade blast design. And last but not least, Mattia is a senior engineer within ARUP Specialist Technology and Research Team. His academic background is in structural engineering, with a focus on earthquake engineering and the dynamic response of structures, and his work in ARUP focuses on analytical and numerical methods for the analysis and design of structures under static or dynamic loading, such as seismic or blast. I think it's fair to say, guys, that we are all very curious to hear what you want to say to us. So without further delay, I'm gonna hand over to Patrizia.
Perfect. Thank you very much, Tina, for the introduction. I'm going to share my screen, just a few seconds. And okay, can you see my screen now?
Perfect, came through.
Okay, let's go to the presentation mode. Okay, can you see it right?
All good.
Perfect. So thank you very much. And thank you all for coming today. So before starting with the presentation, we would like to tell you a little bit about our team and ourselves. So my name is Patrizia, as Tina mentioned, and I'm part of the Resilience, Security and Risk team. And we are all located with my colleagues in London, but in reality in the UK we have also another office in Manchester. And our team also expanded globally. So we have a team in US, one in Singapore, and one in Australia. And we all work together to deliver our services to our client. So Eirini, would you like to introduce yourself?
Sure. Hi, everyone. I'm Eirini. Tina introduced me before. I am a senior consultant in RSR, the same team as the rest of the presenters. I've been with ARUP almost 4 years now, and my focus mostly is on blast design for facades.
Anqi.
Hello, this is Anqi, and as Tina has kindly introduced, and I joined. I'm a consultant from the Resilience, Security and Risk team, and I joined ARUP about 2 years ago, and I mainly work on projects related to design of structures to resist blast loads, and also numerical simulation of structures and explosions. Thank you.
Mattia.
Hi all, I'm Mattia, and as Tina has introduced, structural engineer in the blast team.
Perfect, thank you. So let's start with the presentation now. So the agenda is today is what you see in this slide. I will focus on terrorism throughout history. Then I will discuss about the importance of the risk assessment. My colleague Eirini will focus on protective design strategies, and she will focus on hostile vehicle mitigation. Then Anqi and Mattia will both discuss structural blast assessment, and finally Mattia will finish with non-structural elements plus design. So let's start with the history then. Probably when you came to this talk, you were thinking, why do we need to have protected design against terrorist threat in our asset, in our building? And there are different reasons why we should start thinking about it. And obviously, one of the reasons can be found by looking at history and learning from the past. In fact, in this slide, what we are showing is basically the 1992 bombing attack that happened in London. This building is called the Baltic Exchange, and what happened it was that a lorry exploded in front of it. When we're looking at the picture, we can see that in reality, it doesn't look really too bad. There is not progressive collapse, the column seems fine, but there is something to notice, that is the facade. So just a few panels are still in places. The remaining of the facade was completely destroyed. So although it seems fine from the outside, the situation inside, it is completely different, because definitely there was a severe damage in here. And this was due to the fact that the facade was not blast engineered, and it happened that the pressure could enter inside, and basically the cladding was just detaching, there was fragmentation, and the furniture was completely destroyed. So basically it is not a place where people can come back to work the day after the attack. And now, moving to another example, it's worth noting that this attack, it happened in 1993 bombing, so just 1 year after the one that I previously mentioned. And again, we are in London. This time the lorry exploded in front of 99 Bishopsgate. And it is kind of similar situation of what I discussed before, because if we're looking at the picture on the left, we can see that the structure is fine. There is not progressive collapse. The buildings look okay, but the problem are all these fragments, all this cladding. And in fact, the majority of these fragments created injuries to the people. 44 people precisely were injured during this terrorist attack. And so the lesson learned from the government, it was that before this terrorist attack, there was not really too much attention to what happened in case a bomb happened. So what are the damage that can occur? And after this bombing, the government started posing more attention and they introduced what is called the Ring of Steel. So they wanted to protect the city of London, and also a lot of firms introduced a disaster recovery plan. So definitely it is a lesson learned. And because I discussed about the fragmentation, we thought it was worth in noticing something regarding the glazing. So this is an example to give you an idea what does it happens when we do have something that can resist to blast, that is the right pictures, and when we do have something instead that doesn't have any sort of protection at all, that are the picture on the left. So what happens is basically, when we don't have protection, there are these fragments that are created that are very big and very sharp and definitely can create damage and injury to people. While on the right side, the situation is different. So what happening here, it is an anti-shatter film is applied to the glazing, and an anti-shatter film is basically a plastic film that is applied on the back side of the glazing that hold the fragments together. But this is just one possibility that we may suggest. For instance, another example it is to have a laminated glass. To give you an idea, cars normally have laminated glass. So again, they hold the fragments together and they prevent fragmentation. Another example, this time we are not in UK anymore, so we are in US. It is the 1995 bombing. And it was again a lorry that was exploding in front of the building. So when you're looking at the picture on the left, you can see that the situation is different for what we just saw together, because this time is not only about the facade itself, but also the structure. So we have progressive collapse of the structure of half of the building. And why it happened? It happens because basically the lorry that exploded in front of this column that is highlighted in red. And because this building was not designed as alternative load path, when this column was completely destroyed due to the shock wave, the two columns adjacent to this couldn't basically take the load, so the load could not be distributed, and this initiated a progressive collapse that caused this damage. So again, it is definitely a lesson learned, because we understand that if we have a column very close to a detonation, this can fail in shear, And definitely we do need to have think about having in our design alternative load path in order to avoid this type of situation. Now, another example, how not to mention the 11 September 2001 aircraft impact that I'm sure all of you will remember what happened. So this time is a different type of threat, different from the one that I mentioned before, because we are not speaking about a lorry that exploded in front of the building. We are speaking about aircraft impact that basically brought to the progressive collapse of these two towers. So as you know, there are different type of studies and publications that have been done lately regarding this, the World Trade Center, because it was kind of curiosity, the fact that these towers completely collapse while they have been designed for aircraft impact. And in fact, to be precisely, these have been designed for Boeing 707. And in reality, though, the two aircraft that impacted the towers were almost 20% bigger than the original load that was considering at that time. But in reality, according to the National Institute of Standard Technology, that is the version that I'm going to summarize today, they mentioned that the aircraft was just the first cause that then created secondary cause that led to the progressive collapse of these two towers. So the first things that the National Institute of Standard Technology mentioned, it was that this aircraft had something like 30,000 liters of fuel. 35% of this was just dissolved during the explosion, so basically during the impact. But then we can understand that more than half of the remaining fuel was still in there, and this was absorbed by the level below. This, in connection with the fact that the electricity system was damaged due to the impact, it created fire. And so the temperature became very high, also because the fire was alimented by the fact that the oxygen could enter, as the facade was destroyed due to the aircraft. And so basically the steel beams and columns, therefore, more than their limit, and progressive collapse was initiated. After this attack, it's worth remembering that US published also a new standard, FEMA 426, that basically talk how to mitigate the effect of terrorism attack on buildings. And moving to the last slide. This last slide, in reality, it is the gas explosion that happened in 1968. But in reality, as you can see, it happened before than the example that I mentioned previously. But we have put it in this specific place because it's not an example of terrorist attack. But we wanted to mention in any case because definitely it's something that changed the way we're designing buildings today. And what happened, as I mentioned, it is a gas explosion of one of the topest level that basically led to a progressive collapse upward and downward of this corner. And after this event, what happened it was that the UK standard was updated and robustness requirements were put in place, but actually not only in the UK standard, but also in the American standard and Canadian standard as well. Now, talking more about the present, I'm not sure if many of you knows, but basically there are a level of threat in the UK. Precisely, we have 5 levels: low, moderate, substantial, severe, and critical. These data are public, so you can find these in gov.uk. And at the moment, substantial, it is the level that UK has. And basically, it means substantial that an attack is likely. Another things to noting is also that in the example that I show so far, in reality, I just show example of detonation of bombs apart from the aircraft impact. But in reality, there are also different type of threats. So to mention another one, it is vehicle as a weapons that becomes very popular, more frequent, let's say. And Eirini, my colleague, will discuss more about this specific type of threats and what are the possible mitigation options that we can use to reduce this risk. So coming back to the original question, why do we need to have protected design against terrorist threat? Definitely because of what we learned from the past. That is basically what I show you. but then also because it can bring commercial advantages, because, as I mentioned, people couldn't come back to operations straight away after this event. And then because it is perceived as the responsible things to do, because we do want to protect people and we do want to protect business as well. And finally, because it might protect against potential litigation. So far we have discussed why we need protected design in our assets, in our building, in our infrastructures. But there is another question that probably come up. It is, okay, I need to do something, but how much do I need to do? So how much do we want? It depends. Do we want to have something that looks like a bunker, or do we want something that looks like a building? It really depends on the situation. And how do we decide on the design security strategy? So the response is that we need to do an assessment process model. So this one that I will show now is just an example. There are different types of assessment process model. The first step could be to do an asset value assessment. That means identify if our asset it is a critical infrastructure, for instance, or who is the client, who are the visitor, where it is located. And the answer to all these questions correspond to identify, basically to do an asset value assessment. Then the second step is doing a threat assessment. That it means to identify the type of threat, but also define the type of threats that we can have. Then we have the vulnerability assessment. That means to identify the vulnerability that we can have in our building, for example. And this vulnerability assessment, in reality, is just the first step that will lead to identify possible mitigation options. And this possible mitigation option depends on a cost analysis and on a benefit analysis. And the challenge of all this process is to have all the information and present them in a way that our clients can make an informed decision. A tool that we use very often for risk assessment is called Threat Vulnerability Risk Assessment. That is the one that basically you see in this slide. So it is a live tool, we say it, because it is a tool that is not done only at one stage, but is done in all stages. So it can be done from concept until operation, and is repeated all the time. And it is very similar to what I mentioned before. So again, we need to identify the threat, we need to identify the vulnerability, and then we will end up with a risk level. But this risk level change according with the mitigation option that we're going to use. So this kind of tool, it really helps our clients to focus more on how rather than why. And Eirini will discuss more about how. So she will talk about the security strategy. So Eirini, over to you.
Yes,
you have control.
Thank you, Patrizia. I do. Okay, thank you. So
before we hand over to Eirini, just to say, Patrizia, very interesting presentation, and thank you for that. Just to address two comments that came, and they refer to issues with the screen. We will upload in the coming days the presentation, so you will be able to find the recording there. And if you missed anything, you can watch it online. We will send you the link definitely. Eirini, over to you.
Okay, thank you, Tina. Moving on, so having identified the threats and our valuable assets through the TVRA process that Patrizia discussed, we can start planning for protection. And there's a broad spectrum of strategies when it comes to protecting against terrorist threats. So the TVRA helps us focus on how we can reduce our risks and allows us to demonstrate the benefit of each of the measures that we considered. So in the next few slides, I will briefly talk about the main principles that we follow to protect against terrorist threats. And I'll try to basically answer the how do we protect structures against terrorist attacks that Patrizia said before. So it's a bit slow to change slides. Okay. I think it needs one more click. So first, okay, perfect. So first we can start by disguising our valuable assets. For example, we would avoid having signs indicating the location of a critical facility that supports the operation of our asset, like a control or security room in a train station, for example, or even avoid large signs on the building facade altogether, so that indicate the building's use. Another strategy is by deflecting an attack, and this is really about making the target less attractive and discourage an attacker by making it seem very difficult to approach their target and successfully carry out the attack. And this can be done in many ways, depending on a number of factors, but it usually involves layering a number of security measures. You can see in this picture that there's a line of hostile vehicle mitigation created by some planters, which on a first note create a visual deterrent, but that can be followed by access control and surveillance measures like CCTV, guarding, electronic access control, etc. So making it increasingly difficult to approach and carry out an attack successfully. Okay, we can also try spreading the valuable assets throughout the building, or put them in locations that are more difficult to be accessed by potential attackers. So, for example, away from a main road or a facade where there's a vulnerable facade, like a glazed, large glazed facade, for example. So in the case an attack does occur, the impact is going to be localized and more manageable in terms of recovery after the event. Then we can protect our asset by stopping an attack. And the main way we can do that really is by putting physical barriers and putting a secure perimeter in place. Like in this picture, you can see an example where there's a line of bollards that has been used to achieve that, but there are also other ways we can do that. And we will touch on that a little bit later. And finally, which is what we engineers mostly deal with, is blunt the attack. And that happens by hardening the structure and facade. And while this is largely what we do in our team, it's the last step of the process. So the first three principles can easily be achieved with minimal cost if they're considered in the beginning of the design stages, even at strategic or project brief stage. And that could be done by selecting an appropriate location. So I think that an urban environment may create more challenges. Understanding who our neighbors are. Are we in a risk of being collateral damage to an attack targeting our neighbor? And that's the case for many buildings in London. While they are not a target themselves, being located close to high-profile buildings, they are faced with the need to design in hardening measures and also face the cost uplift that entails, if any. So another way is by using landscaping to our advantage to enforce standoff, and thus reducing the need for hostile vehicle mitigation measures and hardening measures to our structure. And by planning the layout of the building, as I said before, appropriately, so allocating large openings away from a vehicle accessible road, or putting some valuable assets in areas that are not easily accessible. And once we've taken all the actions mentioned at the early stages, we repeat our threat and vulnerability risk assessment, so that to help us understand what are the residual risks and plan for mitigations. And there's a variety of mitigation measures at our disposal. You can see here some of the categories these come under, but the list is not exhaustive. So today we're going to focus on the ones highlighted in red. I will be touching a little bit upon hostile vehicle mitigation, and then Mattia and Anqi are going to talk about structural blast design, and Mattia is also going to be talking about non-structural elements blast design. So one of the first things that we usually look at when starting a project where the need for protective design has been identified is hostile vehicle mitigation. And that's because it serves a dual purpose. So one is to protect from a vehicle as a weapon attack, which is when a vehicle is driven at speed, aiming at either causing injuries to people or damages to assets. And also as a way to enforce standoff from our building and make sure that a vehicle carrying a bomb cannot approach the building, and thus reducing blast loads we need to design for. And this gives us a baseline to calculate the blast design logic. So this is why this is one of the first things that we deal with. And as Patrizia mentioned before, because the weapon attacks have been increasing in the past few years, we've had a lot of incidents last 10 years. Here in London, we've had a few as well. So it is a matter that has been we have been dealing with quite a lot. Here I just want to present a few examples of HVM schemes of decreasing level of protection from left to right, as you can see. In the first picture, we have a scheme that follows guidance from the Center for Protection of National Infrastructure, and it achieves, let's say, their golden standard. We have bollards that are close together, small distances between them, and most of these have been physically tested for vehicle impact, and have been selected to stop the vehicle that has been identified as a threat for the area. So in the second picture, we have a combination of off-the-shelf measures and using landscape features to our advantage, and then a slightly softer approach to hostile vehicle mitigation that mostly create a visual deterrent for the attacker. And I want to put this array of measures because we just have to mention that hostile vehicle mitigation needs to be proportionate to the threat. So we don't really always need to go to these golden standard one. We can go to a softer approach depending on the project and the client. So apart from the threat itself, there is a number of factors to consider when designing a hostile vehicle mitigation scheme. Most of which are mentioned in this slide. And I will not go into this one by one, but sometimes some of these factors make it impossible to specify off-the-shelf impact assessment measures, basically. An example would be the case where we have buried utilities at low depth below the surface of the pavement, for example. And there are no products in the market that can satisfy both the product requirements and have a shallow enough foundation to be placed above utilities. Or another example is where the products on the market do not satisfy the aesthetics of the landscape designer or the client. So in cases like this, we can design bespoke measures to fit the needs of the specific project. So the next few slides, I will focus on one specific case where we designed the reinforced concrete upstand wall. I will describe the process so that you understand what that entails. And okay. Okay, so in this example, vehicle's weapon attack was identified as a credible threat. However, due to some restrictions that we had from the highway authority and the landlord, it was not possible to install measures on the pavement along one of the building elevations. So our client expressed an interest in embedding the HVM into the facade of the building. So we designed an upstand reinforced concrete wall that is in line with the building line, so it's part of the building facade. So as we're looking at a high level of protection, and aiming at no penetration, minimum damage, and we're looking for to achieve a specific rating based on guidance, CPNI guidance. We also conducted impact testing to ensure that it complies and it matches the client's requirements. So after the threat was identified, and that's a common process we follow, we undertook a vehicle dynamics assessment. What we do is identify possible attack paths like the ones you see here, and calculate the expected impact angle, speed, and energy, impact energy for different vehicle types and trajectories. And that sets the design basis. So during an impact, we know that the kinetic energy of the vehicle is converted into work. During a soft impact, the energy is dissipated by the structure. A vehicle hitting a bollard is a good example of that. While during hard impact, the structure is considered rigid and the energy dissipated by the deformation of the vehicle, like in the case of a rigid wall or a planter. In reality, it's a bit of both, but we conservatively here assumed a hard impact to calculate an equivalent static impact force. And based on that force, we undertook a preliminary sizing and reinforcement design, and then moved on to evaluate its performance using a single degree of freedom dynamic analysis. Anqi will talk a bit more about single degree of freedom later, mostly about blast, but it's an efficient way of checking a design is within acceptable limits. So once we're happy with the preliminary design, we use finite elements to model the wall in LS-DYNA to check and refine the preliminary design. So overall, the challenge here was that we had a large level difference between the ground level outside and the slab level inside, creating a large lever arm. And also the need to keep the wall as thin as possible to limit potential damage to the wall itself and not affect the existing slab. So this step was important to provide us with a confidence in the detailed design before moving on to the testing. Again, here we conservatively used an impact force time history. This one you see here, record from a test of a vehicle impact to a rigid wall. So this is applied to the wall depending on the vehicle we have. So a vehicle is stopped by engaging its chassis rails. So the impact force was applied to the wall at the height and area taken by chassis rails. As we know that this was a conservative approach, we also used a modeled vehicle to do the analysis. So we knew that the specific one was a bit less stiff than the one we're going to use on the test during the test. So these worked as an upper and lower bound for our analysis. And we did other sensitivity studies as well that relate mostly with the interaction with the soil. And by we, I mean my colleague James Dilworth, who undertook the LS-DYNA analysis. So after the detailed design was complete, we prepared drawings, pending bar schedules, and sent them to the testing facility who constructed the wall, and we moved ahead with the testing. So here you can see in the video on the left, we have the LS-DYNA simulation, a clip from that, and the actual test footage on the right. And the test result was as expected, where the measure achieved the rating that we were going for. And the performance of the wall was indeed between the two bounds we discussed before. And then was incorporated into the construction drawings. So this was one example of a bespoke design for hostile vehicle mitigation. The good thing that comes out of this is that we have, after doing a few of these, we have enough confidence to be a bit more creative and be able to design measures using analysis. Obviously, we don't always need to go down the test route. That was a client requirement. We are fairly confident in the analysis in order to go ahead with that. And that's all from me. My colleague Anqi will go into structural design for BLAST.
Thank you, Eirini. And I have already requested control. Do I have control? Yeah, I can see my mouse now. Hello, and this is Anqi again. And if we follow the TVRA cycle, as Patrizia and Eirini discussed before, at this point of the design stage, we should have already examined the risks and the threats and the vulnerability of design. But in reality, we still have some risk, residual risk or residual threats left in that process. If those residual threats are related to BLAST, then it is time to carry out a structural BLAST assessment to check the response of the design and how to find a strategy how to protect the assets or the people. Okay, and this slide talks about what we do generally in the structural BLAST assessment. And we typically start from a standard structural design, which is not designed for BLAST. Then, according to the TTVRA report, we can identify the type of loads, so the peak pressure and the duration. And once we can predict the BLAST load, we will undertake a structural dynamic analysis to determine the response of the structural design and subject to those BLAST loads. And if the response or the performance of the structure, either can be a building or single component, are satisfactory, meeting the design criteria, then we don't need to do anything. The standard structural design is adequate. But if the design is not adequate, which means probably a primary structural component is deforming significantly and leading to possible collapse, or the entire building will collapse as a result of our analysis, then we will recommend hardening measures, and we will discuss those hardening measures with the structural designer and the stakeholder. And there are two course of actions after this review and discussion meetings. The first action we can take, or the option we can take, is that the stakeholder probably will accept the level of risk and its impact. So we will accept the structural design and no hardening measure is needed. But if the stakeholder think the BLAST hardening is essential, then we will help the structural engineer or the designer to incorporate our recommendations into their design. And this process is an integral part of the TVRA cycle, and we're helping our clients or the stakeholder to achieve a right balance between the cost of hardening and the value of their assets. Sorry, it's not responding.
I can change it.
Yes, thank you. And what can we use to do our structural design against BLAST? And we have many tools in our little toolbox, and some of them are used for structural analysis, and some of them are used for predicting BLAST loads. But generally, they can be divided into two groups. The first group is what we call fast solving methods, such as the single degree of freedom methods, and for predicting BLAST loads, and we have usually we have empirical methods such as ConVep, and they are based on test data or simple engineering theories, and they are very fast to run and very accurate and reliable for well-defined problems. And we will talk about this in detail later. And at the other end of the spectrum, we have a group of tools which we call physics-based methods, namely finite element methods or computational fluid dynamics. And they are based on first principles, and so it will require a lot of computational resource to run the model, so that is relatively expensive and requires specialist knowledge of setting up the model and also interpret the results. And sometimes it's also require validation of the numerical model so that we can trust the results. And what I'll be talking about is in my following slides are those basic tools we use in our day-to-day practice. And my colleague Mattia will be discussing some more advanced methods and belongs to the FEA group, and namely arbitrary Lagrange Eulerian methods and also fluid structure interaction methods. I'm turning the page. Thank you. And first, let's talk about what options we have for prediction of blast loads. Usually, or the first tool we probably will use is empirical methods. They are based on a collection of scale distance curves, and they are, like I said before, they're very fast to use and very suitable, accurate for mid to far range explosion, and especially if the explosion took place in an open environment and there's no shielding or obstruction between the explosion and the target. And also one thing that is important is that the target's geometry should be relatively simple. And those curves are based on tests of high explosives such as TNT. So what we do typically is we need the peak pressure and the PSO, like showing down the slides, and also the positive duration of the blast loads. We just need the weight of the charge and also the distance from the charge to the target. We can calculate a parameter called scale distance. Once we have that, by reading the curves, we can determine, for example, the peak pressure of the blast loads. And there are many other parameters of a blast wave we can determine using the same methods. The empirical models or empirical methods are very useful and reliable for far range explosion, and but sometimes also for an open environment. But sometimes we will have situation where the explosion took place near or closer to the target, or maybe in a complex environment where we have neighboring buildings would reflect the blast loads, or maybe the explosion is taking place inside of building, so that confinement or the channeling or reflection effect cannot be considered by empirical methods. There is then in those scenarios we should use the computational fluid dynamics methods, and so the safety methods, they have in theory have a wider range of applicability, but it is quite expensive to use. So we only use when we really have to use them. Once we predicted the blast load, the peak pressure, the duration of the loads, and it's time to do a structural dynamic analysis. And the first option, or one of the options, is to use single degree of freedom methods. They are very useful or suitable for well-defined problem. Well-defined means that, for example, a column here and subject to a far-field blast loads. So typically, the column can be simplified as simply supported. Since the blast load is far-field, it can be assumed uniformly distributed along the span, and then the column is expected to responding in flexural behavior. Once we have this simplified system, we can transfer it into a single degree of freedom model. by assembling the dynamic equilibrium equation of the single degree freedom model, we can solve this equilibrium equation and calculate the maximum deformation, also the under rotation, ductility, and also the reaction at the supports. With these results, we can check the performance of the column and then drawing conclusion on the performance of the components. But we are not always dealing with well-defined components like a beam or column individually. Most of the time, we will be looking at the response of an entire building under blast. For example, the steel frame building showing on the slides. And then in this situation, it is we typically use finite element method. And in other cases, where probably we will have to study a response of a column subject to a closing attack by an explosive device. And if we want to see the, or if we want to check whether the column will collapse, we probably prefer to model it as solid elements, using solid elements. And then we can model reinforcement and embed it into the solid elements as beam elements, so we can see the interaction and the response in a bit more detail. I'm turning the page. Yeah, thank you. And this is another example, and just showing how we use a mixture of finite elements to study a response of an attack in the form of an explosive device placed on the floor. So here we want to look at the detailed local damage of the concrete floor. So we assumed we modeled the concrete floor in using solid elements, and in terms for the supporting structures like the beams and the columns, since they are not directly under the blast load or not expect to be heavily damaged, and we typically choose shear elements to model them, and this helps us to reduce the computational demand to strike a balance between speed and accuracy. And this will be my last example, just to show you how we typically choose tools in our project work. And here we are looking at a pedestrian tunnel and subject to an internal explosion. And the explosion took place very close to the tunnel lining. So the structure is made up of 2 layers, and both constructed using sprayed steel fiber reinforced concrete. And in addition to the internal explosion, the lining is subject to a ground water and soil pressure from outside. So our objectives are here are first, we want to prevent collapse, check the response of the tunnel. And then since we did this piece of work at concept stage, and we are looking to provide initial feedback to the tunnel designer. First of all, what tools do we use to predict or calculate the internal loading on the tunnel? And first, we have empirical methods, but they are usually suitable for far-field blast loads and also in the open environment. And this is within the tunnel is a confined space, and the charge is very close to the tunnel lining, and also due to the confinement, we have reflection as well. So it is best typically we will use CFD to model the explosion and the propagation of the load of the blast wave and the loading on the internal surface of the tunnel structure. Once we have determined the blast load, then we face a question of how which tool do we use to analyze the response? As we have discussed before, a single digger freedom model is suitable for well-defined problem. Well-defined means we can expect or assume the structure's mode of response. But here, the structure is very complicated. Also, the explosion is very close to the lining, so we do not know what the dominant mode of response would be. So we choose a finite element method. And in the finite method, what type of elements do we use? We could use beam elements, and we also could use shell elements. And indeed, the static design of the tunnel was done by a shell element. But here, since we have a closing explosion, we are looking at local damage, and also we are very interested in the through thickness response of the tunnel lining. So we decide to go with solid elements. And another point of consideration is that this is at the concept stage, so we don't want to model 3D and detail model. So we opted a plane string approach so that we can just check the most critical section of the tunnel under the highest blast load. We have the results, but as any numerical model, you always get results. What is important is how to interpret the results correctly and use it effectively. At the first glance, we can see in the video, it seems that the tunnel is going to collapse, and which means we have to recommend hardening measures. But if we look at a little bit closer, the potential collapse only happens after the lining of the tunnel is penetrated. Recall that we modeled this using a plane string approach, which means if we can translate this type of local damage into 3 dimension, and we can reasonably expect that the damage would be a mid-sized hole as a result of the internal explosion. And since we have these results, we went back to the tunnel designer and we communicated these results so that they are confident with their initial design, such as the thickness of the lining and also the reinforcement and in the concrete. So they can carry out further design and develop the design a bit further. And in the detailed design stage, we will come back to this problem and create the detailed 3D model and to confirm the local damage and also show that the collapse can be prevented. That's everything from me, and I will hand over to my colleague Mattia.
Thank you, Anqi. I think next slide, please. Thank you. So over the last part, Anqi showed how empirical methods or computational fluid dynamic analysis are used to resolve the blast load, which then in turn is applied to a structural model, which may be as simple as an equivalent single degrees of freedom analysis or some more complex finite element analysis. In either cases, the load is applied as an equivalent pressure to the structure, and so the blast wave cannot interact with the structure. So in this next section, I'll talk about one analysis method across a class of method, which can model explicitly the fluid structure interaction, where the fluid is the blast wave and the structure is our structural model. So in particular, I'll be focusing on arbitrary Lagrange and Eulerian analysis. Next slide, thank you. So why and when do we use this kind of simulations? So this modeling method, this modeling method is particularly useful in the case of near contact blast events. This kind of threats correspond to having an improvised explosive device sitting just next to your structural element. In this scenario, it is likely that the structure will undergo significant damage, and the deformation, the strong deformation as shown in this picture, like here we can see the reinforced concrete column undergoing significant cratering, will affect how the load itself redistribute along the column. So taking a step back, how are arbitrary Lagrange and Eulerian method different from what we are first more commonly accustomed to as structural engineer? So Lagrangian method, which are what we more commonly call finite element method. Then we have Eulerian analysis, which are most commonly associated to computational fluid dynamic analysis. Then we have the arbitrary Lagrange and Eulerian simulation. So in Lagrangian simulation, we have the material matrix, which is shown in blue here, which is coinciding with our mesh, which is actually the spatial domain. Forgive the typo here, the spatial domain. And so when you apply a force, your material will deform altogether with the mesh. On the other hand, on computational fluid dynamic problems, we have a Eulerian formulation of the problem where the material is allowed to move across the mesh. Finally, we have arbitrary Lagrangian Eulerian model where the material can both move through the mesh in a fluid-like manner, so similar to an Eulerian formulation, but also the mesh is allowed to translate and move through space. So as we can see here, like a bullet impacting a rigid shell, at the start of the analysis, the bullet has a kind of Lagrangian-like behavior as the mesh is moving through space, whilst when the bullet impacts the rigid shell, so first of all, the bullet undergoes some extreme deformation, and then the material is allowed to move through the mesh. One final feature, which is very much used in blast analysis with the arbitrary Lagrangian Eulerian method, is that ALE component can be coupled to Lagrangian parts. So to make an example, in the previous animation, so we have our reinforced concrete column where the explosive and concrete are most suitably modeled by an arbitrary Lagrangian Eulerian material, as the explosive is a fluid-like material, whilst the concrete undergoes significant deformation. Therefore, we'll explain later why it's more appropriately modeled as a fluid. On the other hand, we have some linear element, the beam rebar, which would be more suitably modeled as exactly as beam rather than solid element, as that would lead to reduced accuracy of their behavior. Therefore, we can couple them to the concrete that is imposed as zero relative displacement between the two matrices. So then, to summarize, so what are the benefits of the ALE simulation? So we talked about the main feature of kind of being able to have in the same simulation both the blast and both the blast law and resolve also the structural behavior. However, there are also a number of other benefits which are strictly related to modeling of blast phenomena. So first, a typical Lagrangian model. Here we have an example of a composite slab. So on the right hand side we have a Lagrangian formulation of the problem, and on the right we have a Lagrangian Eulerian equivalent model. So typically in the neighborhood of the detonation device, the model will undergo extreme deformation, and the Lagrangian model need to have erosion criteria defined. That is, elements are removed from the analysis when exceeding a certain level of deformation, where anyway they wouldn't provide any strength to the simulation. Why? Because otherwise they would introduce numerical error and instabilities. On the other hand, on the ALE analysis, material can move throughout the mesh. So the problem of numerical instabilities induced by distorted mesh is avoided altogether. What does this imply in terms of having a more accurate analysis? So the ALE analysis, not having to erode material, allows for the mass being conserved, which is quite relevant, especially in transient dynamic problem, where the response of the structure and how critical is the load is strictly related to the mass distribution as much as the stiffness of the system. One another kind of drawback for Lagrangian analysis with respect to ALE formulation of the problem is that element can be deleted before the load is fully transferred. That is, if the element reaches its erosion limit before the full load is transferred, that part of load would be artificially lost. So then, why don't we just use arbitrary Lagrangian Eulerian method or other method of this kind of more complex nature? Well, first, Lagrangian analyses are generally more expedite to set up and less computationally expensive. One other point, which least but not last, is that ALE analyses are generally more prone to numerical instability, so require special care and may require more iteration. So in general, how do we decide when ALE are required or more generally more appropriate, more suitable for the problem? Well, at ARUP we have carried out a series of numerical validation and experimental validation, so that is comparing against literature, but also kind of more simple test and comparison against kind of results available from code relevant to blast analysis. And so based both on this kind of validation exercise, but also based on our engineering judgment, that is, when is the fluid structure interaction or element deletion or one of the items I've been describing relevant, so that an ALE analysis would be more appropriate. So there's always kind of room for the engineer to decide when one method is preferable with respect to the other. So now talking about non-structural elements, as Eirini and Patrizia have previously introduced, blast engineering is not only about structural element, but also about non-structural element, which may be a significant threat over the course of after a blast event. So before going into the detail of design for non-structural elements, it is worth addressing what are the effects, how we can classify effects on people following a blast event. So we have 4 different kind of effects. First, we have the so-called primary effects. That is, consider the detonation of an improvised explosive device. There's a certain radius in the neighborhood of the detonation point where the blast wave would directly impact people and may lead to fatal injuries with a kind of higher likelihood of receiving fatal injury the closest to the detonation point. So we call this radius lethality radius. More specifically, those injuries are related, so first to lung damage, but also to tympanic rupture or abdominal injuries. So then, whilst there's not much which can be done in terms of kind of the blast protective design within the lethality radius, outside that closer vicinity to the threat, there may be other causes for injuries. So here we have secondary effects, which are no structural element or any fragment which is projected at high speed against people because of the blast wave. Then we have tertiary effects, such as people being impacted against the structure, or quaternary effects such as burn, toxins, and asphyxiation. So as blast engineer, our focus when we deal with no structural element is mainly addressing secondary effects. So here we have an example, another example where kind of no structural element have been causing a significant threat to people under the area outside the kind of lethality radius. So just to give an example of how kind of we would address hardening of a no structural element. So first of all, we would consider the load path. So first of all, actually the element, is it ductile? And then we would check whether the connection can withstand the load applied by blast. Then if that is not the case, which could be, as you know, by definition is a no structural element, then we may address the design of these elements by the hardening of this element by designing appropriate tether, which would retrain the cladding in this case from falling onto or being projected against people. So here we would use we generally use kind of energy based method to address what is the strength the tether needs to be designed for. And here I'll pass the presentation to Patrizia again.
Thank you, Mattia. Thanks. So just to summarize what we have discussed today. Today we have started discussing about the threat vulnerability risk assessment, and we discussed about the history, so what happened and the lesson learned. We discuss also about possible mitigation measures. So for instance, Eirini discussed about hostile vehicle mitigation, and she gave an idea of a possible bespoke solution with a wall. And then Anqi and Mattia focus on both structural and non-structural parts by defining different type of tools that can be used. So different type of analysis, single degree of freedom or finite element analysis, or different also way of finding the blast pressure that can be used. So by using empirical model or computational fluid dynamic. But the reality is that this is just one part of many other things that our team does. So for instance, we do facade blast design, ballistic. We have a team that deals with the CCTV, with physical security. So we hope we will cover some of these other topics in another talk. And thank you very much to Tina and to the young second member to invite us today. And hopefully you enjoy the talk. Thank you, Tina.
Patrizia. Thank you, guys. I think you've covered a lot of aspects that you commonly deal with in your daily work, and this is much appreciated from Young Second. Many thanks to Patrizia, Anqi, Eirini, and Mattia. I won't delay that further. I can see many questions in the Q&A. So let's start with the first one. How does the DVRA contemplate the changing threat environment, certainly over the life of the building? That is from Angus Johnson.
All right, so ideally the TVRA normally is done during the life of the building. However, once the building is built, there is a limit that can be done. What is important is to ensure that the design allows for flexibility. So for instance, if we have a column that is critical, this column could be protected. So for instance, could be not in contact directly with the public, or another example could be what Eirini discussed by applying an HVM measure. So this can be something that can be done. Anyone else would like to add anything on this?
I think I'm covered. Just that the TVRA is a live document, really. It's not something we do and then forget about. And with every change in design or circumstances, we need to revisit it in general and act accordingly. Usually, operational security is used, since we cannot really do much about the building itself after it has been built.
Next one from the same person. In the TVRA, how do you advise the client on residual risks that can be designed out, like fatalities from a complex small arms attack against large groups of people around the building? And the supplementary question, does this increase risk acceptance by the client?
So basically what we do is, coming back also to the TVRA, is we are trying to reduce the likelihood. So you remember when in here I was describing where it is, just a second. It's in here. So we were discussing this and we were speaking about the risk. So we have different level of risk. This level of risk, it depends on the likelihood as well. So we can try to reduce the likelihood. This is something that we normally do. But of course, it depends, because it depends which kind of risk we want to achieve. And of course, this also depends on cost and benefit as well. So that's why there is a conversation that we are having with the client and other stakeholders to try to achieve something that is suitable for the type of project that we are doing and to reduce the risk as well. Anyone else want to add? Feel free in case.
No, covered.
Next one then, I think has been covered, but to revise. Are there design standards that are used as part of projects, or are designs bespoke to the risk?
Yes.
I can answer this one. So there are some design standards and guidance that we follow that sets certain limits, but again, but it's really both. So we do go and do the bespoke designs according to the risk. So it's a risk-based approach, the one we follow, but by having some guidance as a basis for the design. Anyone else want to add anything?
No.
Perfect. Next one. How do you keep the TVRA and proposed mitigation measures secure from getting into the wrong hands?
All right. So, okay, first of all, it's not a document that is shared very easily. So normally it's a document that we shared only with the client, so not with the other team, the other engineers that, for instance, are working on the same project, to give an example. And also it depends, because you set kind of requirements at the beginning of the project with the client, because some clients don't want to even have an electronic version. It really depends on projects. So there are requirements that are set at the beginning, and then we follow that. But definitely it is a sensitive document that cannot be shared. Hope it covers.
Next one. Empirical methods provide PI response curves. Does the team believe that all computer models of material response must be calibrated against material testing?
I think most commonly used materials such as concrete and steel, there are reference code, first of all, which provide advice on how they would perform dynamically. So there's always kind of a layer of shared, like, basic understanding of how the material should respond. Then when you enter the realm of nonlinear analysis, whatever that may be, finite element or other, there generally is some extensive literature with different level of complexity, which themselves account for calibrated material model. So there may be a to different level or to a different degree a way to kind of some guidance on what input you should use to model a very specific kind of steel, if that makes sense. So and then finally, just to try and be brief, we do anyway perform validation, such as after having been compliant to the code and having checked the literature and followed the manual with the suggestion, we always perform like a pre-blast analysis. So we do check what's the capacity of the element statically. Is it what we expect? Then we perform or we do have anyway a set of tests, say on more simple tests where we can check if following the series of input we have used, if the output is what we would expect from a more simple method, such as equivalent single degree of freedom method. So I hope that kind of gives an idea.
Yeah, I just want to add that for new materials, we typically are looking for validation and calibration. For example, the tunnel example we showed earlier, it was made of steel fiber reinforced concrete, which is a relatively new material to us. So we requested the structural engineer to give us the material test data so that we could calibrate our model and to increase have some confidence in our numerical simulation.
So I think this also answers the next question. How do you validate the FE analysis results? The next. Oh, Anqi, please.
Oh, I just if we could have we will probably find a contractor or someone to just carry out the test, and we will usually the test will be limited, like the dimension, some parameters will be limited, and if we could have that result and create a numerical model, once we can validate the numerical model, then we can expand the parameters, range of the parameters, and into our design for our design purpose.
Perfect. Next one. What is the team's view on designing for close-in attacks on slabs? You can increase the slab thickness across an entire building, so can a localized breach be tolerated so long as it doesn't lead to progressive collapse?
I can answer that. So yes, of course, we can. We have to tolerate certain damage as long as it doesn't lead to further damages. The only reason why I would enhance the slab in an extended area would be if we had a critical facility underneath that slab. or above in any case.
Perfect. How are the explosive product gases modeled, gas model after the burning accounted for in the tunnel blast?
And the safety software we use the JWL formula to model explosives, high explosives such as TNT. So basically, it's the equilibrium or an equation to control the pressure, density, internal energy, and the temperature of the of a TNT material, and also the air. And what? And the after burn, isn't it? After burn is usually taken care of by adding a little bit more internal energy as the explosion took place. Yep.
Okay. Question from Asana. Have you tried the applied element method modeling for blast analysis? Just curious, as this approach is generally more suitable for extreme loading involving separation of element, software such as ELS, for example.
I just googled what the ELS is, extreme loading for structures. I think I heard the structure, the software before, but we don't have the software, so we do not use that. But we do adopt the applied element method approach in our work. We have conducted research work on precast concrete elements, and we use this same approach to model the connection and the interface between the precast by using springs, so we can have better control of the behavior before we can apply the model in our design.
Okay. I think next question is from the same person and links to a previous one. So if he or she would like to unmute herself and ask exactly what it is about. Otherwise, I'm going to proceed to the next one, but feel free to raise your hand and we will take your question again. Next one, what approach does the team apply to considering the impacts of primary fragmentation, as every device or delivery method will have significant amount of this?
Should I give a try? So usually we primarily consider blast effects, and the explosion was based on the blast. But for if the client requires or the situation requires, we do simulation of projectiles into, for example, we have projects looking at explosion and then projectiles impacting on airplane fuselage. So we do study that as well. Anyone?
Yeah, I guess it was kind of a light touch address of the methodology at the end of the presentation, but always, I guess, based on the level of risk, we have either kind of more detailed approach as Anqi just described, or more kind of simplified ones where we can design. Earlier I talked about the tether, but there may be other method as well, where you kind of assume a failure mode and you check that the failure is kind of within the limit prescribed by certain codes, by first principle method, where first principle are generally energy-based method, as normally the response is not static. So you may, as a first simplification, you may assume that energy is conserved and then derive the kinematics accordingly, or adjust this kind of basic equation to have a quick response on how the element fragment would perform. How far would it be projected?
Perfect. Thank you, Mattia. One more from Fabio. What is the approach followed for existing buildings? Is there any experience that you can share on this? And supplementary question, are there retrofit methods that have been developed specifically for progressive collapse against blast loading?
So I can mention what we do for some existing buildings. So for instance, one way could be to increase the standoff distance, so the distance from the device, from the bomb to the building. So this could be a measure that can be used for retrofit. Or another one could be for the glazing as well. So you remember at the beginning when I showed the anti-shatter film, that basically it is a film that hold the fragments together, and this will also help the building because basically you will not have fragments first, and then you will not have pressure that enter inside the building as well. Then regarding the structure, it depends. So there are some sort of enhancement that I'm thinking of, for instance, could be again to increase the standoff by, for example, applying cladding. So applying cladding to the columns just to the height where a person could be attached to it, could be a methodology. And yes, these are the ideas that I have in mind. If anyone would like to add anything.
And then it's operational methods as well. CCTV trying to limit the possibility of an attack occurring.
And the last one, there is no mention of UFC. In your design experience, how reliable are these expressions? Take them with a pinch of salt as a good guide in design. Any comment on that?
Yes, we didn't mention UFC, but UFC, we do use UFC codes in our work, and it's one of the key publication we always refer to. And actually, the distance scaled curves are taken from UFC. Yeah,
exactly. So the slide that you see now, it basically comes from UFC. So definitely, it is a code that we use with their limitation, obviously.
Yeah.
Okay. And one last from me, if I'm allowed to, probably for Eirini. You mentioned that you saw there's a very interesting physical testing with the bollard. What would be the cost of such a test, not in absolute numbers, but at least in relation to the design work as a percentage, perhaps?
Well, I can say that approximately it would be in the tens of thousands, not too high though, but it depends on what we're testing as well. If it involves building the structure like we did in this case, obviously the cost might increase a little bit. So it depends on construction costs as well, but it's quite a fixed fee for undertaking the test itself.
Perfect. Thanks a lot for the response. I don't see any other questions in the chat, so I think it's time for me to thank again our speakers for delivering such detailed and insightful presentations for Young Psyche tonight. Thanks a lot, guys. We hope
Thank
to see
you very much.
Thank you,
Tina.
Thank you, everyone.
Thank you.
Thank you
very much.
Have a good night.
Good night.
Everyone.
Good night. Bye-bye.
Bye then.
Bye.
Bye.